We're going to look at page 81 to 82 of your book, and it'll look really similar to actually simplifying our radical expressions, but we're going to look at these things called complex numbers. So when we were looking at regular radicals like square root of 25, we know that that is equal to 5 because there's kind of two 5s in there. 5 squared equals 25. So now we're looking at the square root of negative 9. We're trying to think of something times itself that can make negative 9. But because of that negative, there's nothing times itself that would get you something negative. Well, at least no real number. And so what happens is someone created or defined the number I. They said we're going to let I be equal to the square root of negative 1. And then they said, well, that means that I squared would equal negative 1. And so what that number I allows us to do is to actually simplify this square root of negative 9. We're able to say that it's actually equal to, well, 3 should make sense. Square root of 9 is 3. But for this negative, it gets to come out as just an I. And so if you think about why this will work, if we have 3i times 3i, that's going to be equal to 9i squared. But I squared was just defined up above as equal to negative 1. So we can actually say that this is equal to 9 times negative 1, which gets us negative 9 like we needed. So we just defined the new number, I, which gets us to be able to simplify square roots that have negatives inside of them. And at the same time, what we've done is expand our number system. So if you remember, we started by talking about our natural numbers, which were all the numbers 0, 1, 2, and then actually not including 0. Let me get rid of that guy. Actually, natural, sometimes they're called the counting numbers. So you think about when you teach a little kid how to count, you would start with like 1, 2, 3. You don't normally start with 0, and this goes on. And so then 0 was added, and those then became the whole number. So it's all of the natural numbers, but then they also put 0 into it. And then once that was created, then we started talking about some negativity. And so then we said, okay, let's talk about the integers. And so those include all of these whole numbers, but they also have the negative. So we have negative 3, negative 2, negative 1, and forever negative, and then 0, 1, 2, 3, forever. And I said, okay, well, what happens when we take parts of things? And so when we start taking parts of things, then we have the rational numbers. So all of the numbers that we talked about so far are rational. These negative 3, negative 2, negative 1, all these whole numbers and all the natural numbers. But we also have other things like 1/2 or 2.75. It's any number that can be written as a fraction of two integers. But then we realized that there are some things that don't come out so nicely, and that's where we had the numbers that weren't rational. Those are our irrational numbers. And we kind of talked about those like pi and e most recently. And those radicals that just don't come out perfectly, like radical 5 or radical 7. And so these sets of numbers all made up what we're used to and what you've heard a lot, and those are the real numbers. So that's been our real number system. And so when we looked at down below that square root of negative 9 and we said not a real number, we didn't mean that it was like some sort of like fake number, but the name for the other set of numbers that helps us to solve things like that is called our imaginary numbers. And so there are some things that are purely imaginary. And so we could write like 2i and 3i. And so then these are kind of separated. But overall, all of these numbers are inside our complex number system. And every number can be written in this form, a plus bi, where a and b are real numbers. But we have this little imaginary part. So even though we see something like the number 3, this is considered to be in our complex numbers, but we could write it in that form, 3 plus, there's nothing imaginary about it, so 3 plus 0i. So all the numbers that we're used to seeing, if they don't have that imaginary part, we would just have 0i. So they can be written in this form. And so that's what we're looking at when it says we're going to talk about operations on these complex numbers. So if we go on to the square root of negative 27, as soon as I see the negative inside there, it makes me want to pull an I out. And then the 27, that doesn't go perfectly, but we can break that apart. I know that's 9 times 3 and 3 times 3. So I can still pull pairs out and simplify the radicals like I'm used to. And we would have that little 3 still inside. And so remember, our check is that we can multiply 3i radical 3 times 3i radical 3, and we should get negative 27. So if we rearrange this just a little bit, because all of this means we have multiplication between everything, so we can rearrange it. We could write our 3's next to each other, we could write our i's next to each other, and our radical 3 and our radical 3 together. And so you see what we have here. We have a 9i squared. Square root of 3 times square root of 3 is square root of 9, but really you could have just said 3. I squared is negative 1, and we have 9, which all of that equals negative 27. So we found the number, though it's kind of weird, this 3i radical 3 that satisfies what the square root asks, and that is what number times itself makes that inside number. So if we want to do some more operations with those, the big thing again to keep in mind is really the definition of I squared. We always want to replace I squared with negative 1 if we see that. Now I know I is equal to the square root of negative 1. We don't normally replace that. We normally just keep it as that number I, because those complex numbers, again, they're of this form, a plus b with the I. So we're going to multiply just like we did with our radicals. I'm going to write 2i for the row and 3i plus 2 for each of those columns, and just do the multiplication like before. So this will be 6i squared, and this will be 4i. Now remember we said I squared was negative 1, so we're going to have 6 times negative 1, which is negative 6. So our answer, will we write it, negative 6 plus 4i, and we always want to keep in mind that if we are dealing with I, we want our answers to be in that complex number form, which is that a plus bi, and that's what we have. So you should take a pause right now and try and complete questions 3 through 4. See if you can do them, and then come check back in one at a time. So it'll be really similar to what you had done before. But this time we have our I. So now that you tried number 3, I'm going to write, we have 5a minus 3. We have I plus 2. And we'll multiply. This will be 5i squared negative 3i. 10i, and again you're just multiplying whatever the numbers are in your row and your column, and then this will be negative 6. So we know that I squared is negative 1, so we'll have 5 times negative 1, which is negative 5, and I have these guys that have i's on them. We can put those together just like you have 10x minus 3x. So it looks like my answer here will be a negative 5 from that first box. When I put 10i and negative 3i, it looks like that should be like 7i. And then we have negative 6, but even negative 5 and negative 6 can go together to be negative 11 plus 7i, and it's written in that nice complex number form. Okay, we're going to look at number 4 now, and we have square roots of negative numbers. So this doesn't look exactly the same as the last problem, but we can just simplify these, and so that way we'll be able to see our I and basically rewrite them as looking more like our complex number. So the square root of negative 4, you see that negative inside, that's going to be rewritten as 2i. The negative inside here, again, we write an I, but this time that 5 can't come out, so it's just going to say a square root of 5. You can write it as square root of 5i, but I find that sometimes you like extend the bar. It just ends up being a little bit nicer if you leave it in the front, but either way is perfectly fine. And so we're going to take that times, we have a negative inside again, our square root, so there's going to be I, and square root of 9 is 3, so we get that. And then plus, we'll pull that negative out as an I, and then radical 3 has to stay inside. So we're multiplying 2I and a positive I radical 5 times 3I times I radical 3. And so when we multiply 3I times 2I, that's going to make 6I squared. But remember that I squared is negative 1, so we have 6 times negative 1, so we'll get negative 6 here. Then we're going to take our 3I and multiply it with our I square root of 5. Well, this time, the 3 and the radical 5 are just going to sit next to each other. So when we do 3I times I radical 5, so these guys will just sit next to each other, and then we'll have an I squared. But again, I squared is negative 1, so we multiply that with 3 square root of 5, it'll be negative 3 square roots of 5. And then we're going to move down to the bottom box, I radical 3 times 2I. Again, we'll kind of write it out so we can see what happens, times I radical 3. Our 2 and radical 3, they can't actually multiply because they're not both in radicals. We'll just write them next to each other, and then we'll get an I squared. The I squared is negative 1, so we multiply that by 2 radical 3. We're going to get negative 2 square roots of 3 there. And then the last guy, I radical 3 times I radical 5. The radical 3 and radical 5 can multiply because they're both inside radicals, so we'll get radical 15. And then we have I squared, but I squared again is negative 1 times that square root of 15 makes negative square root of 15. So then our final answer here, hopefully, it will be negative 6 minus 3 square roots of 5 minus 2 square roots of 3 minus square root of 15. And none of these are like radicals, so they're not going to be able to combine together. And so that would be my final answer. So then it continues on to ask, what do you think the conditions are for adding and subtracting complex numbers? So you should take a minute to think about that. But basically what's happening is when you're adding and subtracting, you need to have like terms. But this time we don't really have exactly terms. We have our imaginary parts and our real parts. So the imaginary parts can add, and our real parts can add. And this is actually really similar to what we already saw with our radicals, because if you think about it, the imaginary part, that would be the part with our I, is really a radical. So it's going to behave the same way. Okay, so we're going to try and add following what those conditions are. So we have 2I, 4I, and negative 5I. They all have an I, so again, it's all like having radicals. So we have 2 of them plus 4 of them minus 1 of them. So that's 6I minus 5I, which will equal 1I, or we can just say I. So on number 7, and this seems to be a confusion. So on number 7, this seems to be a confusion sometimes with students because you see parentheses, but the parentheses are just saying, hey, look here, we have a complex number. So we're going to still add our real parts. Again, it's an addition problem. It didn't say to multiply. Multiplication would have parentheses right next to each other. So we have a sign in the middle, so we know that we're going to be just adding. And what we're going to add is our like parts. So we're going to add the 5 and the 2. That's going to be 7. Then we'll add the 3I and the 5I, which will make 8 I's. So there's our answer written in complex number form. So just make sure that you add when it says add. For the next problem, it wants us to subtract. So there's kind of 2 ways you could think about this. I like to take the negative to both parts so I don't forget to subtract anything, so I can just see them already with that minus and then just add them. So we see in subtraction before that it means add the opposite. But again, just make sure you are not actually multiplying these two parentheses together. So we're going to take our real parts, that's 5 and negative 2, that will make a 3. Then we're going to take our 3I and our negative 5I, and that makes negative 2I. So that would be my final answer there. Number 9, it looks kind of weird at first, like not in complex numbers, but we see the square root of negative 8, and we see a square root of negative 2, so we know there's going to be some i's involved. Again, a reminder, there's a big subtraction between our parentheses, so we need to make sure that we're going to subtract or add the opposite, is what I just showed you in the last problem. So we're going to start to simplify this first, and then we'll subtract. So square root of 4 is 2. The square root of negative 8 will have an I, and then 8 can't come out, but it can simplify. There's 4 and 2 and 2 and 2, so we're going to have a pair of 2's that gets to come out here. The plus sign is still followed. And then there's a 2 that stays inside the radical. So a little bit neater, that would be 2 plus 2i radical 2. And that's our first complex number minus, let's see, square root of 9 will become a 3 plus, inside here we have a negative, so we know I will come out, but radical 2 can't come out, so it's just going to stay there. So our complex number will be 3 plus I square root of 2. Now again, another way that you could write this, and it's 100% right, either way, just kind of moving some things around, you could say 2 square root of 2i, and here we could say 3 plus square root of 2i. Those are 100% the same, but just make sure again that the radical stops and does not cover the I. So if you like that way better, you can write it that way. So these are exactly the same, just a little bit different ordering there. Again, we're trying to subtract. So if we're going to try and subtract that, you could take the minus to each term, so we can add the opposite. So negative 3 minus radical 2i, and we'll still keep the first one. Okay, so I'm not going to be multiplying, but I do have my negative that went through. So I'm going to combine my like parts. So 2 and negative 3 are both the real parts. That would be a negative 1. And then we have 2 square roots of 2i minus a square root of 2i. That's like minus 1 here. So 2 minus 1 would be 1 square root of 2i. Or you could just say negative 1 plus square root of 2i. And that would be my answer. All right, we're going to skip over to the next page, and this time we're going to talk about multiplying and dividing. We're actually rationalizing. So our multiplication here is the same as what we were doing, but we want to notice a couple special products. So 3i plus 5 and 3i minus 5. And again, this page looks really familiar because we did all of this with radicals, and so it will be similar. So we're going to multiply 3i times 3i, and that makes 9i squared. But I squared is negative 1, so this will be negative 9. Then we're going to multiply 3i times the 5, but that's 15i. And then we'll do 3i times negative 5. That will be a negative 15i. And then negative 5 times 5 will be negative 25. So what's nice here, you can see these are going to cancel out. This should seem really familiar. So we're left with just negative 9 minus 25, which will be equal to negative 34. And so you can see those middles canceled out. And it's, again, because this is plus and minus, and besides that, they're exactly the same binomial, so you're going to get that happening. We'll try it again down here, number 11. A plus a bi, a minus a bi. So a times a, that's a squared. A times bi, that's just a times bi. Negative bi times the a is just negative abi. And negative bi times bi is just negative b squared I squared. But I squared is negative 1. So we're going to have negative b times negative 1. That just turns into, oopsie, squared, a positive b squared. So you can see a negative abi, positive abi, those cancel. And so all that's left is this a squared and a positive b squared. And so this will always happen, that when you multiply these special products in 10 and 11, that the imaginary numbers all went away. So there's no imaginary numbers anymore. And that's anytime you take a complex number times the same exact complex number, but with a negative inside. These guys are called conjugates. And you can see from number 11 that this will become a squared plus b squared. And so this should look kind of familiar, but normally when we have perfect squares, we see a minus. And so when we saw that minus, we said, oh, well, that's the difference of two squares. It'll factor to a plus b, a minus b. Now what we're saying, our new idea, is that as soon as we know about these imaginary complex numbers, before we would say a squared plus c squared was prime. It couldn't factor. Well, it can't factor over the real numbers. But as soon as we start talking about imaginary numbers, it can factor. So if I ask you right now to try and factor x squared plus 9, and so I want you to factor over the complex numbers, which means we can use I. So pause for a minute, try and think about what that would be based off of what we saw above with a complex number and its conjugate. So now that you tried, let's see. Did you get it? This will be x plus 3i times x minus 3i. And so if we want to check it, we can just multiply them and do a little box. You can also just distribute if you like that better, but I like how the box organizes a lot of my information. So this will be x times x is x squared. This will be a 3ix. This will be a negative 3ix. And then we have negative 9i squared. So you can see the middle term cancels like you'd want. So we're left with an x squared. And, I squared is negative 1. So we have negative 9 times negative 1. That's where that positive 9 comes from. So there's our check. And just for fun, try one more. Can you guys factor x squared plus 25? You should try it. You can push pause and try. It ends up being x plus 5i, x minus 5i. And this is all because I squared equals that negative 1 that we were missing with real numbers. Okay, we're going to look at now rationalizing the denominator, but with these i's. So we already talked last time about rationalizing meant that you're going to rewrite an expression with only rational numbers. So now if we have an I, that is not a rational number. I is equal to the square root of negative 1. So basically it's saying we need to, when we rationalize the denominator, we want to be able to get I out of the denominator. So we're going to have to multiply by something just like we did with the regular radicals. And that will be by its conjugate. It's complex number conjugate. So here we have 5 plus I times 5 minus I. Some of you guys might have already learned or seen the shortcut from what we were looking at a moment ago. But this will be a 25. We'll get a 5i minus 5i, and then minus I squared. But I squared is a negative 1, so we're going to get negative 1 times negative 1. That will turn into plus 1. So we're going to have the i's canceling out. So in our denominator, we're going to get a 25 plus 1, which is 26. And the numerator, we're going to multiply. I can make a little box again if you want. This one's just really distributing by a single term, so it's not as bad. 35 minus 7i. So 35 minus 7i. And we're going to write that all over 26. Now, it did say up above to write our final answer in that a plus bi form. So I'm going to separate this kind of ugly looking fraction to be 35 over 26 minus 7 over 26i. And this would be written in that form, a plus bi. All right, we got 2 more left on here. Again, rationalizing. This time it says the numerator. And this one we can't write in the form a plus bi, so we're not going to worry about that part. But we do want to see how to get rid of that minus, that's 3 minus I, the minus I part. So we'll multiply by its complex conjugate. This time we have a few different multiplications to do, so let's write 3 minus I, 3 plus I. So we're going to get 3 times 3 is 9. We'll get a negative 3i, the plus 3i, and then negative I squared. Which again, that's negative 1. We already have the negative, so it turns into a positive 1. And those cancel. So our numerator will be 9 plus 1. Well, really just 10. In the denominator, we're going to multiply out 7 minus I times 3 plus I. And so 7 times 3 is 21. We'll get a negative 3i plus 7i minus I squared. This guy right here is still negative 1 times negative 1, so we're going to still get a plus 1. Now this time our middle terms aren't canceling, but we can combine them together. So it looks like I'm going to have a 21. 7i minus 3i will be 4i. And then we have plus 1. So it'll be 22 plus 4i. And that will be our final answer. We can't write in the form a plus bi because we didn't rationalize the denominator. Okay, so the last one looks a little simpler than the other guys. And there's actually a variety of different ways that you can work on this, but we just need at least 2. So we want to rationalize the denominator, which means we really just need the I to not be down there. Well, if I multiply by just another I, then the denominator would be 5i squared. And I squared is negative 1, so this would become negative 5. So that did it. Remember, if I multiply the bottom by that, I need to also multiply the top. So I'm going to get 7i, so it'll be 7i over negative 5. Something else that I see students do is saying, well, let's multiply by the conjugate. So they want to multiply by a negative 5i, again, top and bottom. Our goal is to make the denominator not have an I in it, so this will work because we'll get negative 25i squared. I squared is negative 1, so negative 25 times negative 1 gets us 25 on the bottom with no I. On the top, we'll get negative 35i. And so we'll get negative 35i over 25. Now the difference between these two, and this requires a little bit more work, is that we can simplify. Both 25 and 35 can be divided by 5. So we'll get 7 and 5. So we're going to get negative 7 over 5i, which is the same as what we got here. Now a couple different ways of writing that fraction, just to be clear. We had 7i over negative 5, but that's the same as if you stick the negative in the front, and it's all the same if you put the I kind of off to the side of that fraction. These are all the same. You use any of them. And that's it.